Microwave bench equipment. First part, series on microwave engineering, lecture number 6.11. Under measurements, microwave measurements, the study is on various methods that are followed, various devices that are used, various arrangements or setups that are made for measuring quantities like standing wave ratio, frequency, guide wavelength, antenna gain, S parameters, etc. at microwave frequencies. Most of the quantities which are mentioned just now, they require the usage of one setup, one arrangement called microwave bench. This setup is in reality a waveguide run, a rectangular waveguide run. Hence, it consists of several pieces of rectangular waveguides connected to in cascade. At one end of the run, there exists source. The source may be a reflex klystron or it may be a gun oscillator. At the other end of the run, there exists termination. This termination may be a matched load, may be a short circuit, it may be a horn antenna, it may be something else too. It all depends upon the quantity under measurement. In between source and termination, several components exist over the waveguide run. Immediately after the source, isolator is placed. After isolator, a flap attenuator, then a wave meter, which is followed by standing wave detector, and then most of the times the termination, ending the bench setup. Standing wave detector, it is a multi-part or multi-component arrangement. In it there exists a tunable probe, there exists a slotted waveguide section, there exists a scale, there exists rack and pinion arrangement. The introduction and description of bench setup. Various devices, various meters that are part of microwave bench. It is given in two sessions. In the first session, mainly the focus is on frequencies and wavelengths that are associated with the microwave bench. Usually the bench is made to work over certain frequency range with a certain frequency band. Depending upon the frequency range for which it is designed, the waveguide run in the bench, it has certain dimensions. We consider frequencies and dimensions of the waveguide run in the first session. Along with them, we also come to know about different components that are normally used, that are normally present in the microwave lab of an educational institution. In the second session, we focus on certain critical parts, critical meters that are parts in the bench arrangement for measuring various quantities. Especially the focus is going to be on wave meter, VSWR meter, standing wave detector, and also some other important components. Before going further, one aspect has to be kept in mind always while studying microwave measurements. Measurements are also studied, they are also made at low frequencies. The devices used, the procedures followed in low frequency measurements, they are quite different from the procedures followed, the devices used at high frequencies like microwaves. It is not difficult to understand for the reason for this difference. The signal at low frequencies, it is characterized by voltages and currents. The measuring equipment at low frequencies, it is based on the concept of voltage and current, whereas the signal is modeled with power. Most of the times it is power along with field or field intensity. Naturally, the measurement procedures and the devices used and the arrangements made, their basis is power and field intensity when measurements are made at microwaves. This aspect naturally leads to differing ideas, differing concepts, differing devices, differing setups for measurements at low frequencies and at high frequencies like microwaves. With this understanding in the background in our minds, now let us move to microwave bench setup to understand, to know its structural features and also to know frequencies, wavelengths, dimensions associated with the bench setup. Now, let us start with a few introductory remarks regarding microwave bench. The microwave bench is a cascaded arrangement of several microwave components. The devices and their numbers usually vary with the quantity under measurement. Certain components like microwave source, isolator, attenuator, however, they are common to all types of measurements. The source used in the microwave bench is either a reflex klystron or a gun oscillator. Both are oscillators. Reflex klystron is a tube, microwave tube, whereas gun oscillator is a solid state oscillator, semiconductor oscillator. In either case, one end of the guide on which they are mounted is shorted, and from the other end, microwave power flows out. In educational institutions, the microwave bench works at frequencies that fall in X band. Here and there, one can also find S band bench, but in majority of the institutions, it is X band bench. The features of this bench are frequency band is X band. X band means 8.2 GHz to 12.4 GHz. This frequency range is called X band. The wavelength corresponding to this band is from 3.66 cm to 2.42 cm. It is already mentioned that bench is actually a waveguide run. It means several pieces of waveguides connected in cascade, one after another. It is a rectangular waveguide. The wave that is used in the bench is dominant mode wave. The dimensions are selected in such a way that the wave exists always in dominant mode only. In case of rectangular waveguides, dominant mode is TE10 mode. The cutoff wavelength is lambda c. It is equal to 2A. In case of dominant mode wave propagation, cutoff wavelength lambda c is equal to 2A and cutoff frequency fc is equal to V by lambda c equal to V by 2A, where A is inner distance between the side walls of the waveguide. There is an expression for cutoff wavelength that is given here. It is equal to 2 by square root of m by a whole square plus n by b whole square. Cutoff frequency is equal to 1 by 2 root mu epsilon square root of m by a whole square plus n by b whole square. These are general expressions. In these expressions, if we substitute m equal to 1, n equal to 0, here also m equal to 1, n equal to 0, we will get lambda c equal to 2a and fc equal to v by 2a. A, B are dimensions of the waveguide. Dimensions and bandwidth of guide. The dimensions of waveguide run A by B are 2.286 by 1.016 cm. These dimensions one can measure using a scale with cutoff frequency equal to 6.56 GHz and cutoff wavelength equal to 4.57 cm. In the previous slide, we have seen lambda c is equal to 2a. Here a is 2.286. This thing one can get by measuring the distance between side walls with a scale. So once a is available, lambda c can be computed And FC also can be computed. FC is P by lambda C. It can be found equal to 6.56 gigahertz, and cutoff wavelength can be found equal to 4.57 cm. As the cutoff frequency of the guide run is lower than lower edge of X band, 8.2 gigahertz, it can pass all the frequencies of this band. What he is trying to tell is the dimensions of the waveguide run, they are selected in such a way that the cutoff frequency is 6.56 gigahertz. But it is meant for the entire bench is meant for working with X band. X band means 8.2 12.4 gigahertz. 8.2 is far higher than 6.5. It is higher than the cutoff frequency. So the bench now can work with X band comfortably. The guide used in the bench setup, it is designated as WR90 by EIA. EIA stands for Electronics Industry Association. Note, W stands for waveguide, R stands for rectangular. 90 is 1/10 of width of guide in mils. Under ideal conditions, the bandwidth frequency range over which a single mode propagation is possible of this can be found as 6.56 to 14.8 GHz. Here the point to be kept in mind is the equipment is designed, it is supposed to work with X band. X band means 8.2 12.4 gigahertz. But dimensions of the waveguide, they are selected in such a way that it carries all frequencies from 6.56 to 14.8 gigahertz. The reason for selecting the dimensions which can handle frequencies lower to X band and also higher to X band is to leave a safety margin about which we discuss soon in the session. Guide wavelength range. The guide wavelength is wavelength measured along the length of the waveguide run, and it ranges from 2.85 cm to 6.11 cm. How this range has come into being can be found using this formula. While measuring the guide wavelength, if you come across a number like 7 cm as guide wavelength, then one can understand easily that it is a wrong measurement. There is something wrong, incorrectness in the measurement process. If guide wavelength is found 2 cm, in such case also one can conclude that certain wrong in the measurement process. Reason is the range of wavelength, guide wavelength is 2.85 cm to 6.11 cm. Now, dimensions support frequencies from 6.56 to 14.8 gigahertz. It is told it is a waveguide run. This is A, this is B. Usually A by B is nearly equal to 2. The dimensions of the guide you can find with a scale. Those dimensions, they are given in the previous slide. From the dimensions, one can find the bandwidth. It is 6.56 to 14.8 gigahertz. But the entire bench is designed to support X band, which ranges from 8.2 to 12.4. So dimensions support frequencies from 6.56 to 14.8, but we use the bench from 8.2 to 12.4. 6.56 to 8.2. These frequencies are not used. 12.4 to 14.8. These frequencies are not used. There is a reason for leaving these margins. These margins are called safety margins. Safety margins are 6.56 to 8.2 gigahertz, 12.4 to 14.8 gigahertz. Cutoff frequency is 6.56 for the guide when Guide walls are made with perfect conductors, and hollow region of the guide is a perfect dielectric. But perfect conductors, perfect dielectrics, they are not available. They are not in existence. What we are available with is good conductors and good dielectrics. As it is not a perfect conductor, as it is not a perfect dielectric, what happens is the frequency is slightly above 6.56. Let us say 6.9 or 7. Let us say 7 gigahertz. This frequency, if you use this frequency, it undergoes attenuation, considerable amount of attenuation. Of course, the amount of attenuation the signal undergoes, it decreases, it falls as you move from 6.56 towards higher side. So attenuation here it may be high, but as you move to higher frequencies, it keep on falling. By the time you are at 8.2, attenuation of the signal may become insignificant. So normally for this reason, frequencies from 6.56 to 8.2, they are not used. It is a safety margin. Same thing applies to safety margin from 12.4 to 14.8 also. It is also a safety margin, but here leaving this safety margin is for different reason. The next mode to dominant mode is TE01. In ideal situation, TE01 mode will have zero attenuation here above 14.8 and infinite attenuation below 14.8. But in case of practical guides which are made with finite conductivity walls and with finite non-zero conductivity dielectrics, the mode TE01, it is not attenuated completely or totally. Some attenuation exists, but it is not infinite. Therefore, there is a possibility for TE01 mode to exist when frequencies are smaller than 14.8. However, the attenuation of TE01 mode, it increases as frequency is decreased from 14.8. By the time you move from 14.8 to 12.4, in practice what happens is the attenuation over TE01 mode becomes very high. So practically below 12.4, there is no chance or there is very little chance for the existence of TE01 mode. Hence, leaving safety margins, it helps us in working with a single wave mode, dominant mode in the bench. Some more points. If the source is a reflex klystron, it is required to be operated in 1 3/4 mode, which only can give maximum power output. To operate 1 3/4 mode, the beam voltage is required to be set around 300 volts and repeller voltage is raised until maximum deflection is observed in the VSWR meter. For operation, the reflex klystron requires several voltages which are supplied by klystron power supply. If the source is gun, it must be operated in the middle of its negative resistance region by varying its bias voltage until maximum deflection is observed in VSWR meter. Gun power supply comprises of an electronic regulator and a square wave generator designed to operate the gun oscillator and pin modulator. The micrometer head provided at one side of the source is connected to a movable shot. The shot has to be maintained at a distance of λ/4 from the source and it has to be moved in and out with the help of micrometer until maximum power output is obtained. Why this λ/4 distance? Consider a transmission line, a piece of transmission line whose length is λ/4. It is called quarter wave section or quarter wave transformer. Now, let us suppose one end is shorted and the source is connected. At the other end, this is input side, input port. Because it is short, there exists a standing wave pattern over the line. The standing wave pattern here, it must be having a 0 here for the short voltage standing wave pattern, and maximum, V maximum over the input pole, V minimum at the load end, V maximum at the source end. V maximum also indicates the presence of open circuit. Therefore, a shorted quarter wave line simulates a open circuit. When lambda by 4 is maintained between short and source output, here your source output is here. Source output, then source is pumping its wave into an open circuit. Because it is open circuit, the source does not get loaded. Otherwise, source may get loaded, there may be some reflections causing difficulty in the satisfactory functioning of the source. After source, there exists isolator. The power output and frequency of the source vary randomly when reflected power wave enters back into the source. Isolator provides sufficient isolation between source and reflections, preventing reflected wave entering back into the source. In the lab, isolator that is configured with 3-port circulator and match determination is usually used. Isolator is followed by attenuator. The attenuator used in the bench setup is a flap attenuator, variable attenuator, providing attenuation ranging from 0 to 25 dB. The amount of attenuation provided by the device can be read from the micrometer scale provided. Some more points regarding another device, waveguide detector. What is the purpose of waveguide detector? Wave is not visible to human eyes. Then how to know the presence or absence of a wave in a waveguide? How to know? Waveguide detector gives information regarding the presence or absence of wave. Now, a few points regarding the structure and working of waveguide detector. It is a diode across a piece of waveguide with a movable short inside. It is designed to detect the presence of wave. For maximum response, short must be maintained at a distance of lambda g by 4. See, lambda g by 4, this is short. Here is crystal. Its output is proportional to power of the incident wave, and hence it is a square law device. Usually output is voltage. This voltage is proportional to the power of the wave that is falling over the crystal. Voltage proportional to power. That's why square law device. This fact can also be used to measure microwave power ratio with a simple ammeter or voltmeter. Various structural details are shown here. Notice the short here is in the diagram, it is fixed. Actually, usually it is a movable short. Some of the devices one can find in microwave lab, they are shown here. E-plane T. This is H-plane T. This is magic T. Match termination, directional coupler, E-bend. One can have H-bend also. If the bending is in H-plane, it is H-bend. But here the bending is in E-plane. That's why it is E-bend. Wave meter, one can see it is cylindrical. Detector, isolator, reflex klystron, detector with short, standing wave detector. One can see so many components in the arrangement called standing wave detector. Here is a slotted section, waveguide. Above this is tunable probe. Output of the tunable probe is connected to, most of the times, to VSWR meter. Here exists some scale. This is rack and pinion arrangement. The purpose of standing wave detector is to make measurements over standing wave pattern. Tunable probe, flap attenuator. This is attenuator, micrometer. By rotating, one can vary the amount of attenuation offered by the device. Bench, entire bench setup. This may be a VSWR meter, wave meter, power supply. It may be power supply of reflex klystron, or it may be power supply of gun oscillator. Some stands are there. The waveguide run is placed over stands. Slide screw tuner. What is a slide screw tuner? It is a device which is able to required amount, variable amount of susceptance. While measuring high VSWR this particular device is used. These are some of the points I want to share with you for right now. To recap, dimensions, frequencies, wavelengths, components, meters that are used, that are part of microwave bench setup. They all are introduced and described. Hope you have a beautiful and wonderful, transformative, enriching learning experience. Enough for now. See you again in another session soon. Bye bye.